Hey class, how are you doing? Let's get back into learning series. Okay, I heard there's a homework question and I will talk about that. But first, let me talk a little bit more of where we left off. Okay, so I have separated infinite series into two categories, convergent ones and divergent ones. And most of these came from the result after we finished our two fundamental, very helpful improper integrals. And we talked about this is a divergent series because p is equal to 1, not greater than 1. That's called a harmonic series. And p equals higher than 1, convergent. And then again, it is about the speed of a decreasing. When you increase the when the denominator increases faster, that makes the reciprocal decrease faster. So these are all convergent series. These are the divergence series. Okay. All right. So what I briefly introduced, but I didn't spend any time on in details, are these alternating series. Why are they convergent? Okay. The first one is pretty easy to understand because this without alternating signs, and you just have p equals to 2. So the alternating sign just gives it extra help to make the sum reach a finite number much faster. Okay? And the alternating harmonic series totally rely on this alternating signs to get to the finite sum because, look, without the alternating signs and a harmonic series add up to positive infinity. So now I don't want to just talk, and I want to give you the formal definition. Okay. So here you are looking at, so this is a section 5, alternating series. So there is a definition to check alternating series to see when they converge, when they diverge. Okay, let's look at a convergent case. So here's a series. Okay. If satisfies two conditions, then the series is convergent. First one. Look at the first part. What the heck does that mean? B sub n plus 1 should be less than or equal to B sub n. In my everyday language, I want the terms without alternating signs. Okay, you see the alternating signs are separate. In everyday language, I want the terms to get smaller and smaller. That's number one. Second one, limit of the nth term is equal to 0. What does that mean? That means when you reach the nth term, for example, look at our geometric series, my favorite example, of course. Okay. Look at our geometric series. Take a limit 1 over 2 to the n when n goes to infinity, 1 over infinity, 0. What does that say? That is saying when the term gets really, really tiny. So look at our alternating series. If I want to apply the second part of the condition for the alternating series to be convergent, that means I need to make sure limit of 1 over n as n goes to infinity equals 0, which we satisfy. Okay, all right. So that's the condition for checking out your alternating series to be convergent. Your terms had to decrease to shrink in size, and towards the end, they have to be very, very small. And with the help of alternating signs, then you're going to have a convergent series. So now we can add on to this. For example, we talk about the series to be divergent. Okay. What if I give it a boost and let's attach alternating signs to it? Okay. that's going to make it a convergent series as well. So converge, 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 as long as the nth term to be so small, approaching 0, and the terms had to shrink in size from one to the other. Okay? So now you are saying, oh, Ms. P, that's not fair. This one didn't need the extra credit. It was already convergent. And these two need the extra credit of alternating signs to be convergent. Is it a difference between the two? Yeah, by definition, we do have separate names for the two categories. Okay, all right. So how do we name them? So we're going to separate the two here. First of all, they all converge. This red pen doesn't work. So we're looking at the alternating 2 series. Okay. Oops, didn't come off. All right. So one more time. Without alternating signs, the 2 series is a convergent series. And with alternating signs, in everyday language, that means it makes it more convergent. So this is called absolute. Why is that? Because without the help of alternating signs, this 2 series converge. Okay, all right. Then what about the second tier? It only converge with the help of alternating signs. These are called conditionally convergent. Okay. They are convergent with the help of alternating signs. Reason? Harmonic series as well as reciprocal of Ln, and they both diverge. Okay, all right. So there's a level of convergence now. Yeah. And this will show up in problems that we're going to do, and I will bring this up, and I will keep on helping you to remember this. You don't need to worry. Okay, all right. So let's leave it like this, and let me answer the homework question, and then we'll go to move forward to section 8, power series. Okay, and the homework question I heard that is number, let me see, what number was it? Number 59. Thank you for trying, and let me solve this with you. Okay, homework question, and you should always let me know what I can help you in terms of answering homework questions. Just let me know, and I will do it. All right, here we go. So here's a homework question, and that is still in 11.2, and that's number 59. Let me find mine. Terminologies. Right away, you notice there's a variable x involved in addition to just discrete variable n. And this is actually called a power series, which is the new topic I want to start today. Okay. And if you remember what we talked about, the center for this power series is going to be at positive 2. Okay, I will talk about that again a little bit later. Right now, just concentrate on solving this problem with me, because we are looking for the sum and we are looking for the radius of a convergence. So we need the leading term, we need the ratio. I usually play safe, open it up a little bit, expand with me. Ready? N equals 0, 1 plus sign. N equals 1, plus sign, n equals to 2. And going forward. Okay. Writing this out helps me to identify leading term is 1. I will need it a little bit later. And ratio equals. Right. Let's set it up to find out where this power series converge. Okay. Here we go. So this is a geometric series with a constant ratio. Set absolute value of a ratio to be less than 1. Plugging our ratio. Let's multiply 3. Open inequality. Plus 2 everywhere. Okay, so this is the window of opportunity for this power series to converge. Okay, look at it again with me, centered at 2. That's right. 3 actually is called the radius of a convergence, and maybe I should write it down. Huh? The book is not going to introduce the terminology until section 8, radius of convergence. Okay, centered at 2. I think that's pretty easy to look at. All right. Okay, let's come back again. So I am going to write your x is going to be between -1 and a 5. Okay, and so let's set up. And the numerator is supposed to be leading term. Denominator should be 1 minus ratio. Okay. And the leading term is just 1. Ratio is this rational expression. Okay. And we will clean this up. We're going to simplify rational expression here. I suggest you keep parentheses around x minus 2. Let's multiply common denominator 3 everywhere. Reduce. Write it out. You want to make sure you distribute negative into the parentheses, please. Okay, finish off. So this is a homework 59. Okay. Going forward, I'll tell you what we're going to do. Next section, next topic, I should say. Okay, and we will learn. We will study the interval of convergence. Okay, and we will check end points at these two ends, x equals -1 and x equals +5. Okay, and once we get to that, then we'll have interval of intelligence. So here's a homework problem answered. Take a sip of water, and I'm going to start the new section, power series, which will be difficult and fun. All right, let's move. Okay. Okay, so to begin, what does a power series look like? Okay, all right, so maybe let me write the expanded form first, and then maybe you can help me to write it as a sum, because going forward, being able to write a series, come up with a series, find the pattern, that's quite important skill to have. Okay, all right, follow me here. So suppose I have a series already expanded. C sub 0, C, you can think about C as coefficient, okay, plus and you can always, like, that's all they have, right? If you don't see what's going on, you can always make up some more to help yourself to identify. Okay. And then going forward, of course, equals, let's write a sum. Okay, index n. I myself usually label things that is just much easier for me to identify who is what. I recommend you do that at the beginning. So this is n equals 0, and 1, and 2. Usually it's easier to look at when the terms gets higher, and you see the 2 here. N equals 3. Okay, all right. So these two are much easier to identify. This is not bad, and you know this is a 1. What about this one? Does the C sub 0 follow the pattern? Yeah, it does, because it is x minus center to the WebEx. Yep, that's right. Okay, all right, now you can write it out. So you start from 0, goes all the way to infinity, of course. And it's going to be C sub n. Think about C as a coefficient, not related to x. Okay, so here is a power series. Okay, all right, now take a look at the book, centered at A. Okay, and then also there's a simpler case when center at the 0. So take a quick look, and I'm not going to write it down. So this is also power series. The only difference between the one that Joe and I just did, between that is what we just did, and this is actually, in my humble opinion, simpler format of that, because center is at 0. Okay, power series centered at A, power series centered at origin. Good. All right. Very good. Now, what am I going to do with power series? Okay. All right. For any given power series, there are 3 possibilities. converge everywhere. So the example you and I just did, power series centered at 2, that's right, converge to this rational function in the small window from -1 to 5. Okay, that's the one we did. So in comparison to the theorem, to me, this is like the case 3. Okay. There are also problems. The series converges everywhere, the whole real number line. Series converges at the center. Series always converge at center. So there are 3 cases here. So how do I find out who converges to what, and when, and how, and stuff? And what we're going to do is we're going to use ratio test. Okay, ratio test. Let me tell you what it is. Okay. Do you need a break? If you need a break, take a sip of water. Reorganize. Okay, come back in. So I have given you the details of a ratio test as well as a rule test in your handouts, that stack I gave you before spring break. Okay, followed by the definition of power series, ratio test and a rule test. I didn't teach you these 2 sections, these 2 topics, because they are, and you can see in the book where it is, and then in section 6. But you are so smart and you're so hardworking. I don't think we need to break up into a separate section and teach you separately. I'm just going to use it in the power series section, and we're just going to learn as we practice. Okay, and there's a lot of information. All I need you to do is to remember the first part. Okay. And ratio test. You take a limit of the ratio, take a look at what's inside the bars. It's a term divided by the term beforehand. So this is just like the ratio in our geometric series. Okay, so you're like, oh, then why don't they just use a geometric series? Well, too bad. No series have constant ratio to be a geometric. So this you can use the ratio test for any series. Okay, all right. And then that's just too much information. I myself, I only remember if it's less than 1, limit of a ratio if it's less than 1, and then you have absolute convergent. And also notice the limit. N goes to infinity. What does that mean? That means we are looking at the comparison of the 2 terms, which is we're looking at the limit of the ratio. Where? At the very end of the series. Not at the beginning, not at n equals 1, not at n equals 10, at the very end of a series. Okay. All right, so also there's a root test. Okay. And again, I recommend you just use your precious memory to remember the first condition. If this is true, and it's absolutely convergent. Okay. All right, so I think the best way to do this is just to start working problems with me, shall we? All right, deep breath. We begin. Example. Find the radius and interval of convergence. Here is a power series. Look at the coefficient part. That is the C sub n. That is the part without x involved. And you notice the alternating signs. Okay. And then the variable part. Okay. Since this is the first problem, let's write the problem in terms of a definition. Okay, ladies and gentlemen, so center equals +3. Okay, C sub n, that's the part of a series without variable x. So that's alternating signs over 5 to the n. Okay, and you notice this is an alternating series in its own right. Okay, and the ratio is -1/5. So that's a convergent one. Okay, but right now don't think about that. Let's apply the ratio test. Apply ratio test. There's going to be a learning curve right here, but I will hold your hands and I will help you through. Okay, definition. We are looking at the very tail end of the series. That's what the limit means. Absolute value bar, and it's the ratio of a term against the term before it. So this is just like the ratio of a geometric series. Okay, and we're going to use that on our power series. They call it A sub n, and that's fine. Equals limit. Okay, all right. So first of all, so it's going to be a rational expression, and the look at our power series is already a rational expression. So I usually do, especially if it's the first or second problem, I usually write some extra step. So I'm going to keep numerator like it is, and I'm going to times the reciprocal of denominator. And you don't have to write this out. You can think about this step. Okay? We are looking at very end of the series. And we don't want to be bothered with positive signs, negative signs, therefore we use absolute value bars. Okay. First challenge, how do I write a sub n plus 1? So all of this is a sub n. In order to write n plus 1, first of all, you need to catch all the n's. How many here? 1, 2, 3. All 3 n's need to be replaced with n plus 1. Okay? All of 3. Nothing loose, nothing hanging. That's my favorite thing to say. Alternating signs, n plus 1. X minus center, n plus 1. Denominator, also n plus 1. Times the reciprocal of a sub n. All of this is a sub n. Reciprocal is just write as a reciprocal. Five to the n in the numerator. Alternating signs. X minus 3 to the n. Okay. All right, ladies and gents. From here on, we just need to reduce this. Okay, and this is a good place to practice our algebra technique, especially with exponents. So if you have any weakness there, and just work a little bit harder, or let me know, or both. And I will do enough problems so you feel comfortable. Absolute bar. Okay. And I'm myself an organization freak, you know me. So I'm going to prepare 3 groups, the alternating signs, the 5s, and then the x minus 3s, because that's how I cancel. Okay, start with the alternating signs. Denominator, let me use my ruler. Alternating signs, so it's 3 packages here. All right. Alternating signs, open up, -1 to the n, -1 to the first. Partner, -1 to the n. Already you see how you cancel. Okay, you only need to write this if you need to, but you don't need to. You just go ahead and reduce. Same. I'm going to write 5 first. Sorry. So numerator 5 to the n, denominator open up, not x. Denominator. All right. And we cancel out what we can. Woohoo! Clean up, my favorite. Okay. And let's write what's left, and then we reorganize. Okay. So right now, just take a step. Hey, did I cross out the wrong one? I did. I am so silly. 1 and now I fixed it. Okay. All right, so let's see what's left. -1 and x minus 3 and 5. I'm going to look at absolute value first. Okay, so absolute value will knock off this -1, and the 5 doesn't need absolute value. So absolute value will be applied to x minus 3 because x is a variable. I don't know where it is. Okay, and the second part, hey folks, you notice there's no n anywhere? None. So how do I take the limit? Well, you just take the limit. You don't change anything because I don't see n anywhere. Okay. Now you're going to bring this guy out. Finally settle it down. So absolute only sticks on x minus 3, and limit is taken. No change is made because I don't see no n anywhere. All right. So this is the application of ratio test. Now let's look. What do they want from me again? They want, can you see? Yeah. They want the result to be less than 1. Didn't we do something else? Also absolute value, something less than 1? That's right. Geometric series, absolute value ratio has to be less than 1. Do you see the connection now? So I want to set it to be less than 1. I'm going to force its hand to be convergent. Okay. So now I just need to solve this. I'm going to write it up here if you don't mind. Okay. So I have absolute value of x minus 3 less than 5. Right away, write it out. Radius of convergence equals 5. I learned this from solutions menu. They say radius of convergence equals 5. Okay, and what's next? Next, we're going to let's find interval of convergence. Interval of your solutions menu calls it interval of convergence, super cute. All right, let's go find it. So first we'll solve inequality. Okay, begin. Again, center data 3, radius 5. Open. Plus 3 everywhere. All right, ladies and gents, if you need to take a quick water break, okay, I'll wait for a few minutes if you need to. Ready? Okay, back in the game. All right, so let me make sure negative 2. Okay, now going forward, we will check endpoints. Okay, and let's check x equals negative 2 and x equals positive 8. I want to know what happens to the series at exactly x equal to negative 2 and x equal to positive 8. So we're going to replace negative 2 and a positive 8 into our power series. Okay, plugging. So plugging. Alternating signs. 5 to the n. Negative 2 minus 3 to the n. Okay, and I usually do assembly line and do the other one at the same time. Alternating signs. Okay, and first step is to clean it up a little bit. If you get tired of writing n equals 0 to infinity, during the process you can just drop it, you just write a summation sign. Okay, right. Alternating signs. Okay. Multiple ways of simplify this. I myself always work the same way. It may not be the most convenient, efficient, but always gets the job done. In addition, there's an extra technique I want you to drill with me. So could you put up with me negative 5 to the nth power? Would you write as alternating sign and then playing 5 to the n? Okay, it's just one way of reducing this. I know, they cancel out. Okay. And I'm going to go on with the other one. Okay, now they are at the same level. Write your equal sign. Okay, I'm going to clean up some negative 1 to the 2n. Okay, and can you help me? What is -1 to the 2n? What is -1 to the the even exponent? -1 to the 0, -1 to the squared, and -1 to just a regular 1. Okay. All right, now let me add index back in. Okay. And that one already had index on. So let's open it up and see what's going on. Remember, if a series is a convergent series, you need to add up to a finite number, a number like 1 or 10 or something. Okay. All right, let's see what's going on. N equals to 0, 1, plus n equals 1, 1. N equals to 2, 1. Oh, can't stop. We know what that is, right? I'll let you think about it. I'm going to go on to the other one. That one I wrote twice today, since yesterday. N equals 0, n equals 1, n equals to 2, and 3. If this is many you're going to take, you're going to have a 0. But what if I take one more? So this is a divergent end. Okay. And what about here? You keep on adding 1 non-stop, you're going to add up to positive infinity. So ladies and gentlemen, and everybody, both diverge. All right. So let's report our answers. For radius and the interval of convergence, radius of convergence equals 5. Okay. Interval of convergence equals, let's see. So I know from -2 to +8 is my interval. 10 units. Okay. All right. Let's look at the end of a -2. And this is a interval of convergence. You see the C here stands for convergent. Okay. And if when we check the x equal -2 end, if it's convergent, and I would use bracket. But here I'm not convergent, so I have to open it up. Okay. Again, at x equals 8, again you see the C stands for convergent. If at x equals 8, your series happen to be converged, then I will use bracket. But we are not convergent, so we use parentheses. Okay, this problem is done. So it would take many more for us to feel comfortable and also knowing what's going on. So here I just apply the ratio test. And what I'm going to do is I'm going to do the same problem again. This time I'm going to interpret the same problem as a geometric series. Okay, so here, method 1. Apply ratio test. Okay. And I'll do the same problem again. And I'm going to apply geometric series. And we still will, let's just find radius of convergence. Okay, all right. And we're going to interpret this as a geometric series. So this is method 2. Okay. All right, so first let's make sure it is a geometric series. How do I do that? I want to open it up. Alternating signs. Huh? N equals to 2. Next one should be negative. Okay. All right. So now let's think about geometric series. Leading term is what? 1. And ratio. Okay. And obviously it's going to be x minus 3 over 5. Positive or negative? Can you help me? Must be negative. Isn't that right? So you start on 1, multiply this, will get you negative. And you start the n equals to 1 term, multiply common ratio, positive. Yeah, make sure there's a negative sign here. Okay. All right, so how does it work in geometric series again? When does it converge? We're going to set absolute value ratio to be less than 1. So let's just apply that. Okay, all right. We solve absolute value equation. You can take out the negative sign and you're going to multiply 5. Okay, and did you notice we arrived at the same place? We had the same result when we did ratio test. This faster, huh? Yeah. So you would have gone, then we will go through the same drill, okay? And this is the radius of convergence. And now how do you do interval of a convergence? Same, exactly the same as we did earlier, okay? All right, and still you would check endpoints. Let me keep a note here. From here, same as method 1, interval of convergence. You still open up both ends because we checked. Okay. So you're like, well, what's the advantage? You end up the same answer. Why would you do 2 different ways? If the series is a geometric series, then there's advantage to using it as a geometric series that ratio test that didn't provide. If it's a series, a geometric series, then not only you're going to find out when the series converge, and also you can find the sum. That's the best part. Okay. All right, follow me here. Got too excited, I banged my head on the lamp. So when you are in the interval, that's only 10 units. Is that right? 5. That's all right. 12 units here. 12 units here. You will have a sum, okay, as leading term leading term is 1. That's what I want to write. And then 1 minus ratio. And that's ratio. Okay, one more time. leading term over 1 minus ratio. And this is the result of geometric series we talked about earlier. Okay. We need to clean this up, so maybe write extra step is just too weird right now. Double negative. Okay. We multiply 5. And we have our result. Numerator is 5. Denominator is x plus 2. Okay, so not only we find out where the series will converge, it will converge to this rational expression. Okay. So I want us to talk about 1 split second of what's center and the radius of a convergence. So where is center for this problem? Center at 3, centered at 3. Okay, so what is this radius and interval convergence? So starting from 3, and the distance between your x and the 3 is 5 units. So we go 5, okay, and the 5. Okay, so and this is 3, 4, 5, 6, 7, 8. And this is 2, 1, 0, negative 1, negative 2. Okay. And that's 5 each way from center. Okay. All right. Only when, so this is x-axis. When, so you have a series, x could be whatever you want it to be, okay? But if you restrict your x between negative 2 and positive 8, this infinite process, you keep on adding and adding and non-stop, this infinite process will have a finite result. It adds up to a finite sum, and the finite sum is, see the expression, it's a rational expression, okay? So what's the connection between this rational expression and this power series? Your power series will act just like this rational expression in the window 10 units here between negative 2 and 8. They behave exactly the same. Okay? So the beauty of that is if you have a rational function, and then you can do all cool calculus things, you can differentiate, integrate, whatever you can find. So the other side of this game is to start off with a rational expression, see if you can write it out as a series. So that's another level of this topic. I don't know if I have any more time left, so maybe not. Let me check.
We should definitely wrap it up.
Okay, all right. Thank you so much for your time. Yeah. Oh my God, I'm so lucky today.
Yeah, so, well, I'll go stop the recording. I didn't know if you wanted to do any last things before we, do you want to, okay. So, let me go